So, welcome to the second session of the computational physics lecture in the workshop. So, we will now work hands-on on Julia and see how it works, how it doesn't, where it is spectacular, where it is a spectacular failure. We will see all of the above. I'll give you a brief intro about what Julia is, and we will work with that. So let's just go back to where we left in the presentation. And Julia is a 2009. Julia development started in 2009. It was conceived by these four gentlemen at MIT, and the original goal was to make a high-speed, high-level language, but they ended up with a high-speed, high-level language which is very versatile. And how versatile is it? Now we know government systems take time to change. In fact, uh, the postal systems of several advanced countries in the late 2000s were still running on Windows XP. So it is a great surprise to me when the US Federal Reserve stopped using MATLAB for its simulation purposes and started using Julia. Now, why did they do so? Because Julia is a sleek, lean, mean fighting machine, right? Now, MATLAB loads all packages, all subsystems at boot up, and at every time a program runs in or a script runs in MATLAB, first it must select which booted up subsystem to call and then make that call. And that makes it slow. That is one of the reasons why computer algebra systems are slow. While in C and Java, C is very fast, but C has a very big problem. The problem being it has no packages. It has no additional functionality. If you want complex numbers, you have GSL, and if you want higher precision, it is not worth doing in C. Java is slow itself. So Julia is fast because unlike other languages, Julia is written in itself and it evaluates commands in real time. So that is why it, it is so fast. Now, Julia is a community driven project. So your experience with Julia will depend on what you want to do with it and how we're using it. So let's just give you a comparison. Uh, so the faster the language is, the more close this spread of dots will be, and the lower it will be towards the lower end. So see, C is having just one dot. So that is because it is taken as the standard. Julia has a small spread and it is on low range values. So are these four languages. So Fortran is slower than Julia and a lot of tasks. Java is even slower. JavaScript is even slower, which makes sense because MATLAB and Mathematica run on Java and JavaScript. So if Java and JavaScript are slow, they will be slower. Now Python is slightly faster than MATLAB and Mathematica, and it contains a good amount of functionality as well. R is the less I speak, better. It's so slow. And Octave, with the exception of one task, which is matrix multiplication, it does all other tasks very slowly. So what does this show us? That Julia is not only fast, it is fast across lot of tasks and is comparable with C, and it has a lot of additional capabilities. So we'll see the Julia's capabilities in these three parameters: base language, uh, graphical data handling, and symbolic computation. So in this demo, I'm just concentrating on what is different with Julia. So I'm not covering the entire thing. So let's start the demo. I'll boot up Julia. Julia is booted. Now, thing is, in normal programming languages, you have arrays. You have to first declare the array type and you have to declare the array size. But here you can do that quite easily. So this is defining array as a row vector or row matrix. If I wanted to do a column matrix, sorry, this is a column vector. I can do a row vector like this. So column vectors are separated by comma, elements are separated by commas, row vectors elements are separated by spaces. So writing a matrix can be quite tedious in languages, and I'm here using the base Julia language. I'm not using an IDE because Julia IDEs differ from version to version, differ from OS to OS. So this will give you the base vanilla features and you can apply it everywhere. So I can do A star B, I can do multiplication, and I'll also get results. Now, say I was doing C, I had this vector C. So, right now, assume this is quantities of items I'm buying, A, and C is prices of the items. So, suppose I wanted to find an itemized bill, what I would do is, what do I need to do? I cannot multiply two column vectors. So I do something known as use something the broadcast operator, which is simply the period C dot A. I get this thing, and if I want to do uh, this even better, so let's suppose I want the sum also. We can do this via sum C dot A 32, which is the exact sum. Now, moving on, we will try to do a little bit of plotting, data plotting, and see how that is see how one can calculate a large swath of data very quickly. So this is one way of defining an array. I can also define an array as a range like this, where it runs from 1 to 0.101 into 10 pi. Yeah, I can give pi, I can type in pi like this. How do I do that? Backslash pi tab. Cool, right? So now this x has this many variables inside, and it ranges from 1 to 3.7. Now let us take y, and in y I want to plot the sign. I want to record the sign of each value of x. So I will do this sign broadcast operator x, and I'll suppress output because it takes too much screen space. Now I suppressed output. How do you know that it has taken the sign of every value of x? Well, The proof is in the plotting. So what do we do to plot? We use a package called plot. So this takes time, and this is one of the sad points of doing computational physics videos. Sometimes initializing takes time, and there's nothing we can do about it. It's just a part of life. This is not my main machine. On my main machine, which is a desktop, this runs quite faster and smoother. Uh, so yeah, so we are done now. We can plot. So let us just plot. So this is the plot command I'm using. Plot x and y. There's tuple where y-axis is plotted is mentioned second, x-axis is first, using the label sin f x. So this is just any string label. So now it is started plotting, and you will see it does not have a plot window. So nothing will open here. You will get a pop-up in which the graph will be there and displayed. So that will be clear in a few minutes, in a few seconds, sorry, time. Yeah. So the pop-up has come. So I'll just share that pop-up with you where in the video. Yeah, the pop-up has come. So you can clearly see that my data range starts from 1 and it goes to something like 30, 31, which means that it is running from 1 to 10 pi and everything is fine. This is clearly a sinusoidal curve. So can I do something even funkier with this? Yeah, I can. Suppose I want to add another line on this plot. So let me say y1 is equal to cos dot x, right? And suppress the output. Then I can use this statement. Now, this statement I will have to change and make it y1. Otherwise, it will give me undef var error. And obviously, the label also needs to change to cos of x. If we execute this, what we will find is that, sorry, present this. Yeah, so I've added another layer. So now I'll just show you the result, and the result will be something like this pop-up. You can see clearly, you can see there's a lag between the sine and the cos term. The cos term lags behind the sine term, and it is evident for us to see that this is working and plotting properly. So the next thing that we have to discuss is SymPy, or the symbolical Python front end, which is useful in Julia for doing symbolical calculations. So I will do using SymPy. Now this will take a little bit of time because I am loading all the libraries that are required for the running of SymPy. symbolical languages. Now SymPy is loaded. I can start with my next task, which is quite easy, by the way. Uh, so the next task is to define x as a symbol rather than a variable. So how do we do that? The syntax is quite simple, and there. Now if I type, whenever I have to take what a variable is, I can simply do type of x x sim. It's a symbol. It is not a variable. So if I do sine x square, what I'm getting as my output is sine square x, not evaluating. But suppose I wanted to put some value. Suppose I want to generate some nice type format. What will I do? Well, I can do something like this. Okay, it didn't get copied. Just bear with me. So we use the subs command, and instead of f of x square, we use the previous, use this thing. Now I can even make a change here if I want it for a stylized value. Yeah. So now for this, I can evaluate sine square x. This is the way I give to evaluate sine square x. So what all can you do with this? You can do limits, you can do integrations, and you can use limits, you can use integrations, and you can do expansions and simplifications. So I will, since we are discussing functions, let us do limits and integrations itself, and that will give us an idea of how to do. The rest is pretty self-explanatory, but how a limit works is a little different here. So this is the first limit every student who comes to this point, up to this point, learns. Limit of sine x by x as x tends to 0, 1, quite accurate, right? And let's see an integral. So we do this way. We want to integrate cos square x indefinitely. We get x by 2 plus sine x into cos x divided by 2, which is the actual value. So this is all how you can use SymPy, how can you use Julia. And with this, I would like to conclude this video, and I'll see you in the next video where I will use Julia for actual physics solving problems. So I take your leave.